Hello guys. As promised, I'll be doing some recap of the IEEE single floating point conversion in arithmetic. Before you start, you should first of all, of course, know how to do regular binary arithmetic. So I won't explain in depth how to do it. Of course, you'll see me do the progress or the process of, for example, adding binary numbers or multiplying them. Anyway, but it's up to you to make sure that you know how this is done before taking up the IEEE single floating point conversion and arithmetic stuff. What's important here, so let me do a small recap what you should know about the IEEE. So we have the IEEE, and in our case we'll be doing the single precision floating point. Yes. So what we need to know about this before we can start is the layout of IEEE single floating point. So if I draw, for example, a piece of memory, you know, or you should already know by now, that it is divided into three parts. So the first part in the beginning of the format is what we call the sign bit. So remember that the IEEE conversion or standard uses one complement notation. So this is not a two's complement. This is important for addition and subtraction. So I'll go over that in a minute, what the rules are for that. And so the sign bit uses, like the name says, it's one bit, so it has the size of 1. Then after the sign bit, we use 8 bits to have our exponent. So as mentioned during class, the IEEE single precision floating point or double precision floating point is basically just a scientific notation, just like we know it in decimal representation. So nothing special there. So to be able to have this scientific notation, we need of course an exponent, and then the other 23 bits are what we call the mantissa. So the mantissa and the exponent are being used to write the floating point in a scientific notation. Now, so if you can do the math yourself, of course, this single precision floating point, or float in C++, is 32-bit in size. So that's important as well. Now there's one more catch here. There's one thing, and it causes some confusion. Inside or in between the exponent and the mantissa, so basically right here, we have what we call the implied bit. So the implied bit. And we don't write that implied bit, like the name says, it's implied. But basically, if we write down the mantissa, we'll see in a minute, so like this, 1 point, and then 1, 0, 0, 1, 1, 0, for example. This here is the implied bit. So let me take my marker. So this is the implied bit. And so if we store everything inside the mantissa, we ignore the implied bit. So we just write down 0, 1, 1, 0 instead of 1.0110. But so this is the implied bit. And if we talk about normalizing stuff or normalizing the mantissa, this always means that we match the mantissa so that it starts with 1 point, so that it starts with the implied bit, so that we can discard this single bit before storing it into the mantissa component. Yes? So, the first thing I want to do with you guys is doing the conversion of a decimal number to IEEE. Then I'll be doing some arithmetic, so I'll do addition, subtraction, then I'll take a look at the arithmetic of subtraction and addition, but with different signs, because that's important because of the sign bit, because of the ones complement. And then I'll be doing one exercise on multiplication and one on division. Now for division, I'll use, so for the addition, subtraction, the conversion, and multiplication, I'll be using the same two numbers, operand A and B. I'll show that in a minute. But for the division, I'll take the example that we did during class. I'll show you the result of doing the division with the two numbers I will use for the other exercises or the other parts, but you'll see that I avoided it because it's a little bit more complicated division. But I'll show you anyway. So you'll see that the thing I'll be explaining is exactly the same thing for any two numbers given to you. So the two numbers I want to convert and use with you guys is 0.85, and I'll call this my operand A, and the other one is 1.25, and let me call this operand B. You'll see that I'll be doing the conversion right now, and then I'll just refer to them as A and B, and I'll be rewriting their binary representation on each page probably, so I can easily extract all the information when needed. Again, you don't need to know the exact decimal number to do the arithmetic. If I gave you two hexadecimal values or two binary representations of IEEE single precision floating point numbers, it's fine that you just have that binary representation, so you can do the arithmetic and then converting it to a decimal number. You don't need to know the decimal representation of the two operands to be able to do the arithmetic. So that's one thing. So yeah, let's start with doing the actual conversion of the first operand being A. And oh yeah, one more thing. If I write A and B, what I basically am writing, and that's important for the subtraction and the addition part, basically we have plus A and plus B, because both of them are positive. So I'll be using, so if I write A, I basically mean plus A. This is important for the, again, the subtraction and addition part, where the sign bit, the ones complement, is pretty important. But I'll go over this in a minute. But so the conversion itself, so let's start with A. We need to know the three parts to be able to have our IEEE notation of that number. So I'll be starting with the simple one, and that's the sign bit. So the sign bit of A, that's pretty easy. It's basically saying, is it a positive or a negative number? In this case, it's a positive number, so I write down a 0. If it would have been a negative number, we just flag it with a 1. It's easy as that. And then we have the exponent that we need to calculate, and of course the mantissa itself. And so to be able to do this, we cannot calculate the exponent before we calculate or extract the mantissa. We need to do them simultaneously, basically. What I need to do is, first of all, start calculating the mantissa. And if we take a look at it, we can basically divide our number into two parts. First part is an integer part, so everything before the radix point. And in this case, it's pretty simple. It's 0. So the binary representation of 0 is, of course, 0 itself. And then we have the fractional part. So everything behind the radix point or the decimal point. And I already showed you the technique for this, and it's pretty simple. I write down the number without the integer part. So basically in this case it's the same number, it's 0.85, and I multiply it by 2. And then I get 1.7. And then I take a look, and if it's 1 or bigger than 1, I store a 1 in binary. And then I just discard the integer part and reuse that fractional part and do the same thing again. So 0.7 times 2 is 1.4. So again, it's bigger or equal than 1. I store a 1 in binary. And you keep repeating this process until you reach 0. So when you don't have anything left, that means it's a finite number. It has a finite representation. Or it can also be an infinite representation. And what we do then is we take a look until we have a repeating part. So I'll just keep doing this conversion like I am used to. So 0.4 times 2 is 0.8. It's smaller than 1, so I store a 0. 0.8 times 2 is 1.6. It's bigger, I store a 1. 0.6 times 2 equals 1.2. It's bigger than 1, store a 1. 0.2 times 2 is 0.4. It's smaller, it's a 0. 0.4, and now here you should be able to spot that we have a repeating part. So from this moment on, I'll be repeating this pattern 0, 1, 1, 0, 0, 1, 1, 0. So we basically have our solution. So this is the repeating part. Now don't make the mistake, you cannot discard these two. These will be notated, of course, and then we have the part that keeps repeating. So my fractional part is 1, 1, and then 0, 1, 1, 0, 0, 1, 1, 0, and I'll just add 3 points to say this is repeating. Now the next step is writing both of them, the integer part and the fractional part, next to each other with the radix point in the middle. So I write 0, which is the integer part, point, and then 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, and so on and so forth. Now by default, this is being written with an exponent of 0. So this is our result. Now, as I mentioned before, we need to normalize our mantissa. It needs to start with 1 point. So in this case, to have this representation, what I can do is, or what I have to do, is I need to shift my radix point 1 times to the right. And of course, if I do this, I get this result, 1.10, and then I get, so 1, 1, 0, and then I get 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and so on and so forth. But because I shifted the radix point, just like with scientific notation, I need to take this into account with my with my exponent. Yes, and so if I want to, and that's the thing you should think about, if I change the representation, I always need to be able to get the same representation back. So basically my exponent will become -1. So I shifted once to the right. If I want to have the same value here, and I shifted the radix point to the right, I need to shift it back to the left. So I have to do -1 to have the same representation. Yes. Now, so this is almost our result. There are 2 more things we need to do. First of all, so we know our sign. We also know the exponent by now. It's -1. But you have to know that the exponent in the IEEE format is an unsigned representation, which means we cannot have negative values. Even though the exponent, of course, can be both negative or positive. It's pretty common to have negative exponents. So to be able to store it in a way that it is compatible with the unsigned representation, what they did is they biased the exponent. And so you basically shift your range with a fixed number. In this case, it's the half or almost the half of what you can store. And so to be able to bias your exponent, the only thing you need to do is you need to take your exponent, -1 in this case, and you need to add 127 to it. And then you get 126. So this, let me take another pen. So this, our -1, this is our unbiased exponent. And this 126 is our biased exponent. And so each time you extract the exponent from the IEEE format, it is biased. So if you want to use it, you need to unbias it, and of course you can simply do that by doing -127 instead of +127. But if you want to store it, you need to bias it. And so 126 in binary is 011111110. So this is the exponent in binary that we will store inside the exponent component in our IEEE format. So we're almost there. So the next step you do is you take all the information you have, so the 3 parts, which are these. So the one we just calculated, and then the mantissa, so 1.10, and then so I'll be writing, by the way, instead of writing it like this, you'll see me often write it starting with 3 bits, so 1 point, then 3 bits, and then I continue writing everything down using per 4 bits or a nibble. This is just a little bit easier because, as you can see, I can count how many bits I have by just taking this one. So I know this 8 is twice a nibble, and then the 1, and then 3 bits, again a nibble, and then it's easier for me to count. So you'll see in a minute, it's why I write it like this. So this is our mantissa. So what we do then is we write everything next to each other. So we start with the sign bit, which is 0, then the exponent, which is 0, 1, 1, 1, 1, 1, 1, 0. And then I write down the mantissa, but don't make the mistake, you have to write it down without the implied bit. So I write 1, 0, 1, so 1, 0, 1, and then I'll repeat until I have my 32-bit entire representation of the number. So 1001, 1001, 1001, 1001. So I have 4, 8, 12, 16, 20, 24, 28, and 32. But remember, this is a repeating part. So basically, this is my imaginary boundary of memory. I can keep writing 001, 1001, 1001, 1001. And it's important to write it one more time using that barrier for yourself, so it's easier to see what the storage itself is. Because one of the things is, if we have a repeating part, we need to check if we need to round the number. We also discussed this during class. There are multiple rounding schemes, but we'll use the standard one, the common one, which is, and let me say, so what we do is we take the number, in this case, this one, so the repeating part. So I write down 1001, and I'll write down what the decimal representation is, which is of course 9, and I divide it by, and that's pretty hard to explain, I'll divide it by the next most significant bit value. By that I mean I'll divide it by, I put everything to 0, and I put a 1 in the next most significant bit, which is of course 16. And what I do if I want to check if I need to round it, so I said I'll divide it by that. It's not true. It's for the converting it back. So sorry for that. But I'll do the same thing. I'll take the 16. I divide it by 2, which is 8. And then I'll take a look. I have 3 options here. If my result, if for example 9 is bigger than 8, which is in this case it is, then I need to round up. 2, if 9 would have been smaller than 8, I would have done nothing. So I would do nothing. And third case, of course, if it is equal, for example, if this 9, this result, would have been equal to 8, then the standard says in 50-50% chance that it rounds up. So 50% chance it rounds up, or 50% chance that we don't do anything. And so to be able to do this, of course, it's pretty easy. We just take a look at the least significant bit. If it's a 0, so least significant bit. If it's a 0, we don't do anything. If the least significant bit is a 1, then we round up. So that's the rounding scheme. And so in our case, of course, it's the first one. 9 is bigger than 8. So this means I need to round up. So the last part, I'll just add 1 to it. So rounding up is just adding 1. So this becomes 1, 0, 1, 0. And there you have it. This is your IEEE single floating point representation of the value 0.85. So we have our exponent, our biased exponent, we have our sign bit, and then we have our mantissa that has been rounded correctly. Et voila, that's how you do it. So let me do the second one with you guys. So something like this. So our second number is 1.25. So I'll do the same thing. I'll write down the sign bit of 1.25, which is of course again 0. It's a positive number. And then I'll be calculating the exponent and the mantissa of b. So again, I'll start with the integer part. In this case, the binary representation of 1 is of course 1, which is pretty easy again. So if it would have been 40, you just write down the binary representation of 40. And then you again calculate the fractional part. And so I'll do the same thing that I did before. So I'll take the fractional part, which is 0.25, 0.25. I'll multiply it by 2, which gives me 0.5. It's smaller, or it's not, it's smaller than 1, so I'll write down a 0. I'll take 0.5 times 2, which is 1. And of course it's equal to 1, so I store a 1. And now I'm done. I don't need to take care of that. I'll have 0.0 left. We're done. So here we had an infinite number, or infinite representation. Here you can see we have a finite one. So these are the two possibilities you can have when converting. So this is our mantissa. This is our fractional part, 0, 1. And then I'll do the same thing. I'll just write them down next to each other. So 1.01 in an exponent of 0. And I'm pretty lucky here because it is already normalized. It starts with the implied bit, so I don't have to do anything. So cool. So the only thing I need to do now is I need to write everything down, and of course I need to calculate my exponent because, again, this exponent here is unbiased. So what I have to do here is, again, just add 127. So 0 plus 127 equals 127. And this is our biased exponent. And of course the binary representation of 127 is 0, 1, 1, 1, 1, 1, 1, 1. And then I write everything down. So I use all my components. And so it starts with the sign bit, which is 0, then the exponent, which is 0, 1, 1, 1, 1, 1, 1, 1. And then I'll write down the mantissa without the implied bit. And so I start writing down 0, 1. And then I don't have anything left, which of course means I can fill everything up with zeros. So 0 and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, until we have, of course, 32 bits. So it's 4, 8, 12, 16, 20, 24, 28, 32. And there you have it. This is the binary representation of the IEEE single floating point value of 1.25. Of course, we don't have to check if we need to round the number because it has all zeros, so it's pretty useless, of course. So there you have it. So this is part 1. This is converting your decimal numbers to the IEEE single floating point binary representation. So next up is the arithmetic, and I'll be keeping a short pause on this video because I had some issues before, and I'll be back in just a moment.